Hello everyone, thank you for joining this ROS tutorial section on ROS and ROS2 using MATLAB and Simulink. Hi, my name is YJ Lim, Technical Product Manager for Robotics and Autonomous Systems at MathWorks. Today I will begin by introducing ROS capability from MATLAB and Simulink. Then I will discuss about ROS and ROS2 workflow. And then I will show you ROS application example using MATLAB and Simulink. Finally, I will summarize what we discussed today. Let's dive into ROS capability from MATLAB and Simulink. You can connect ROS and ROS2 from MATLAB and Simulink for design and development of robotic autonomous systems. With a live connection from MATLAB and Simulink to existing ROS network, you can explore available topics, services, and actions. This allows you to send command to and receive the data from any simulator, hardware, or software node on the ROS network. MATLAB and Simulink also provide the utility to work with common sense data types such as laser scans, images, and 3D point clouds. If we are using decoded data from rosbag file, our toolbox allows you to read these files for post-processing or playback data as a simulation input. After initial testing, you can automatically generate C++-based executable ROS node from your design. These generated nodes can be integrated with ROS and ROS to build a system so they can run on your target system with no dependency on MATLAB and Simulink. Alright, so what ROS functionality we offer today? As you can see, there is support for both MATLAB and Simulink workflow, although they are not quite same. A key difference is code generation. It only works from Simulink model today, although we have some workaround to do and future plan. ROS2 interface is fairly lightweight, but it covers the most common user cases. You are able to do the pop and sub with ROS2 from both MATLAB and Simulink, and also generate standalone ROS node from Simulink model. For both ROS1 and ROS2, you can generate your own custom message. In our 2020B release, we support both ROS1 and ROS2 all major operating systems. At the moment of 2020B release, we support melodic LTS for ROS1, dashing LTS for ROS2 respectively. We replicate ROS command line tool, so if you are already familiar with open source ROS, you could adopt MATLAB API function easily. Let me talk about ROS and ROS2 workflow with MATLAB and Simulink. ROS is enabling technology to develop complex intelligence systems. With a given system design requirement, ROS provides a common framework to design, simulate, and prototype robotic application. With ROS, you can analyze log data, design algorithms with various hand return code, and visualize and debug your result. You may need to rewrite source code for production though. By connecting MATLAB and Simulink with ROS, it allows you to perform system-level simulation with design requirement traceability. It provides rapid and iterative design process with many of the tools MATLAB Simulink has for autonomous systems. You can also generate certifiable code for production. Now, let's see how we bridge ROS with MATLAB and Simulink. In the right-hand side, this is how traditional ROS-enabled system might look like. There is a host of ROS-enabled simulator and hardware, and through the ROS network, they can communicate with a node that would enable autonomy, visualization, and so on. In the left-hand side, MATLAB Simulink offers tools for autonomous system development. For autonomous system development, systems should have functional component of perception, planning, and control. And now we have a type bridge to ROS from MATLAB and Simulink. There are basically three workflows. First is data analysis and playback. You log the data from simulation and hardware and then want to bring them into MATLAB Simulink environment for offline design task. Next is desktop simulation. This will be a live connection between ROS and an instance of a MATLAB for algorithm development. And finally, deployment. The same implementation you may have used for prototyping can be automatically generated as a standalone ROS node that you no longer require MATLAB to run. I want to point out, beyond just the bridging ROS with MATLAB and Simulink, you can complement traditional ROS solution with MATLAB and Simulink tooling. So now let's take a look at each workflow with some example. In offline data analysis workflow, the typical use case is to import data from simulator or hardware to better understand the target system, or maybe to prototype algorithm. For example, you can read a batch of images for labeling and training neural network. You can extract specific topic from time-stamped data to synchronize and visualize them. The ability to read rosbag file and to work with specialized ROS message types for sensor allow you to bring all your design data into MATLAB and Simulink without need for a lot of pre-processing code. For sign detection example, you can use computer vision and deep learning to automatically learn image features. Here you can label image topics for detecting sign. And you can use laser scan and odometry data imported from rosbag file to create the map of environment. In this example, we use SLAM Map Build app from Navigation Toolbox to map the environment using LiDAR scan topic. Let me switch to MATLAB and show you rosbag example. In this hands-on section, I would like to discuss about how to import rosbag file recorded and how to select ROS topic that we are interested in. You can also access and filter information from rosbag file in MATLAB. First, we do some initialization. To view the information about ROS logo file, use rosbag info file name. Here we use a rosbag file that we recorded with the sign following robot example. You can view the detail of information of ROS data, such as available ROS topic. Let's load TURBO3 the bag file using rosbag command. You can also examine all the ROS message in rosbag file. In here, we have an array of images that contain image topic. In the same way, we have an array of scan that contains scan topic. To evaluate available topic that are recorded in the bag, you can do bag available topic, so you can see all the available ROS topics. Now let's extract image topic. In here, I want to read the actual ROS message data into MATLAB. Depending on the size of your selection, this can take a longer time and consume a lot of your computer memory. In here, I'm only extracting first the image topic message using read message function. You can also take out an entire image typing message and play them in here. We use deployable video player object to display the video frame and video file writer object to write video frame. Similarly, we extract an entire scan typing message and plot them in here. We create 2D LiDAR scan object out of range and angles. Now let's look at how we use laser scan and odometry topics imported from rosbag to create the map of environment. In this hands-on demo, I will introduce you the SLAM Map Builder app from Navigation Toolbox. So SLAM Map Builder app can help you build occupancy grid map from laser scan data interactively. So you import and filter the scan data and odometry topic from rosbag file. Here we use the same rosbag file decoded from same following robotic example we saw earlier. You can specify the parameter such as scan topic and odometry. You may also select desired start time and end time depending on the environment you are interested in. Because laser scan may be captured at a high frequency, it will be a good idea to downsample the scan to reduce some processing time. Now we are ready to move on the building the map of environment that robot visited. You can also set and tune the SLAM parameter here. These values can be adjustable based on your sensor specification, environment that you'd like to map, and then your robot application. Then let's begin to build the map using scan topic. You see that scan being overlaid in the map. And also the estimated robot trajectory is plotted on the same scan map. In the right-hand side, incremental scan match of two subsequent frames are also shown in this incremental match panel. If you notice the map is distorted, you can pause and select that specific scan to adjust them. This is very important, so you can interactively optimize and to create accurate the map of environment. Finally, you may see a poorly overlaid and optimized scan map without trajectory that robot went through. You now can save the final occupancy map of environment as occupancy grid object. So now robot can use this map for many things such as path planning and obstacle avoidance. Second workflow is ROS network and communication. Your autonomous algorithm can be prototyped and evaluated by connecting ROS network to external simulator or hardware. Here, I'm showing a sign following robot again running on Gazebo simulator with a Simulink in the loop. Sign detection algorithm is running on Simulink. It may be either simple image processing with color detection or more advanced deep learning algorithm than you saw in the previous slide. And velocity command will be published through ROS network to control a robot. We have a virtual machine image that you can download. It has ROS1, ROS2 installation there with several examples you can try out. MATLAB Simulink make desktop simulation easy with ROS together with many other design tools to test and verify new robotics algorithm. Let's take a look at a simple MATLAB and Simulink interface workflow. Within the MATLAB, you can create ROS network and participate in existing ROS network. You can then collect the data, send and receive the ROS message. Your algorithm can be processed to schedule execution of a MATLAB code efficiently. Then you publish your command to control your robot. Then you can visualize your simulation result. Similarly, in Simulink, you need to set up the sum configuration to establish the connection with ROS. And then we have a control loop, which is continuously sensing the data of a network, and then doing some kind of a processing of an algorithm, then sending out the command or control signal back to your robot through the ROS network. One thing to note here, you see this block that I highlight which include ROS in it. These blocks are ROS blocks coming from ROS Toolbox to read the data, subscribe the topic, as well as create a message and publish ROS topic. These blocks allow you communicate with ROS without writing any code. Okay, let me do another hands-on section for controlling Turtlebot 3 from MATLAB. This example is about connecting ROS with MATLAB using Turtlebot 3 ROS package. First of all, we use a virtual machine that has ROS melodic installation with Gazebo simulator. In the Linux terminal, we source ROS melodic setup bash, which telling we are going to use ROS1 melodic distribution, and we use Turtlebot 3 WafflePi model in Gazebo simulator. Then finally, we launch Turtlebot 3 Gazebo package with a Turtlebot 3 world example. In another terminal, let's launch teleop node to control Turtlebot by keyboard. Then you can use a keyboard to move around in a Turtlebot in Gazebo world. You can try another node available in Turtlebot 3 Gazebo package, for example, collision avoidance, slam, and so on. Okay, now let's participate ROS1 network from MATLAB. We will need to shut down any existing connection to ROS. Then define the MATLAB IP address. Then you can find by typing ipconfig from command prompt. And let's define ROS master IP that Turtlebot is running on virtual machine. Then we set the environment variable, then finally to connect to ROS master. You can see topic available in ROS network from the MATLAB. You can see the command velocity and the camera in the topic as well. And you can also subscribe odometry topic and see the detail as well. Let's create image topic subscriber to see what robot is seeing. Now we can display an image stream while controlling robot to move around. We have a velocity command publish here and set up the angular velocity of 0.1, then send over velocity command over ROS network. In the meantime, we saw now an image topic that we have received. So you can see image stream while Turtlebot is rotating around in Gazebo world. Finally, node generation for deployment. Verification is an important task. Your robot algorithm needs an evaluation with a simulation over real robot hardware. You can manually port your algorithm to work on your target system. Alternatively, you can control do this process with ROS Node Generation. This can speed up development process and remove manual implementation error. Once you have generated ROS node from Simulink, there are several ways you can work with it. For example, in Simulink, you can use external mode to tune the generated ROS node in situ, even though the code itself is running on target computer. It can be a good debugging tool while you are still designing your algorithm to tune the parameter and visualize the data directly in Simulink model. Now that we have a good idea about the capability offered by ROS Toolbox, let's get into a couple of application examples. The first application example that I'm going to show is a sign following robot. The robot, the Turtlebot 3 in this case, will identify posted sign and follow them to the given destination. We develop sign following navigation algorithm in Simulink and utilize ROS2 network for communication. We will use Gazebo to simulate the Turtlebot 3 and environment. Simulink model controlling the robot will receive the image and odometry data published from Turtlebot 3, compute the velocity command, and then send them back to the Turtlebot 3. Note that this setup illustrates a powerful concept. You can develop your navigation algorithm, test and verify entirely in simulation environment. Since we are moving in virtual environment created in Gazebo, we are allowed to make a mistake. For example, the robot can hit the walls. This might be catastrophic in real life, but it is an opportunity to improve navigation algorithm in simulation. Once we satisfy that algorithm works as intended, we can easily deploy the Simulink model as a standalone ROS node to run on real hardware. Now let's get into detailed workflow steps. What you see on the right side is Gazebo simulator running on Ubuntu virtual machine. This virtual machine is shipped as an add-on to the ROS Toolbox. In main window of Gazebo simulator, you can see the environment and Turtlebot 3 robot. Now in MATLAB, I'm going to set up an environment variable called ROS domain ID. ROS2 uses DDS as transport layer. DDS supports physical segmentation of a network based on the number called domain ID. In order to interact with one another, two ROS2 nodes need to be on the same DDS domain. In this example, we set up Gazebo simulator to create DDS domain with ID 25. First, let's create ROS2 node in MATLAB. Note that we specify 25 as the domain ID. We can now talk to robot running in Gazebo through this MATLAB node and dynamically discover, publish, subscriber, and more using ROS MATLAB interface. We can get a list of available topics in ROS2 network using ROS2 topic list command in MATLAB. Let's dig into the ODOM topic. First, we create a subscriber to receive the message from ODOM topic. Can access latest message and display the XYZ coordinate of robot position. We can send the command to the robot as well. To do this, we create velocity publisher. The publisher also provides an empty message of the type geometry message to with. We can set the angular velocity to 0.75 radian per second and watch our robot rotate around the g-axis. To stop the robot, yes, just reset the angular velocity to 0. Now let's take a look at Simulink side of workflow. As of our 2020 release, ROS Toolbox support deploying Simulink model as a standalone C ROS 2 node. Since one of the objectives of this application example is to deploy navigation algorithm as standalone ROS 2 node, we will be using Simulink to develop the algorithm. On the left side is Simulink model. It uses the camera image and odometry information as an input. We have an image processing subsystem that identify and track the sign. Here, blue sign for left turn, green sign for right turn, and red sign for stop. In this example, we use a simple drop detection to extract the color, dust, direction information. Let's learn Simulink model. As you can see, velocity values are being constantly updated. You can also go to the Linux terminal and view the message directory. For example, you can view the detected blob information published from Simulink model. You can easily analyze what your model is doing by peering into the state flow diagram. Debugging your algorithm in Simulink environment is a lot easier than debugging hand-written C++ code. Here you see our robot reached the stop sign successfully. Okay, everything seems to be working as we expected. What do we do to deploy Simulink model as a ROS node running on the virtual machine? We go to the Apps tab in Simulink toolbar and click Robot Operating System. Select ROS 2 as a target. This brings up the new tab called Robot. We go to this new tab, make a change in the hardware simulation configuration as needed. We then click on Build button to generate the code from our Simulink model. Got generated. In our source folder, we have a complete ROS package configured to work with ROS to build a system. Now we take this package to our ROS 2 workspace in the Ubuntu virtual machine. We open terminal window and build the ROS package. We can then run standalone node without MATLAB and Simulink. While this node is learning in virtual machine, we can kick off a companion Simulink model for visualization. We can display what robot is seeing by receiving a message published on image topic. We can also look at velocity command and start and stop the robot as desired. While we built the ROS node in virtual machine, we could just easily take the ROS node and load it onto the actual robot. What we do in simulation environment can be extended to the real hardware. This is the beauty of ROS design framework. Here is our second application example, automated parking valet. This example has 4 set of subsystems differentiated by the use of MATLAB with ROS or ROS2 and Simulink with ROS or ROS2. Parking a car autonomously is a challenging problem, and there are various ways to tackle the problem. This example demonstrates one way of realizing automated parking assistant. There are several core modules required for navigation problem, such as behavior planner, path planner, controller, and vehicle model. Each one of these core modules are represented as a separate node on the ROS network. Nodes communicate with each other by standard publish and subscribe message. For simplicity, this example focuses on planning, control, and vehicle modeling. We use pre-decoded data to substitute for localization information. There are 4 core modules in Simulink model: behavior planner, motion planner, controller, and simplified vehicle model. There are feedback loops from vehicle model to controller through the behavior and motion planners. Behavior planner read current vehicle pose from ROS2 network. It computes waypoint and check if vehicle has reached the final pose. The motion planner computes a feasible path through the environment map. Desired trajectory is sent to the controller, which calculates the steering and velocity command to move the vehicle. Single parking valet model can be broken out into 4 separate models to facilitate deployment as a distributed system. Simulink signal line going in between various modules are replaced by ROS publish and subscribe blocks. Motion planner, for example, calculate and send the desired trajectory to the controller of the ROS network. And we can then deploy behavior planner, motion planner, and controller as a standard ROS node running on actual vehicle and replace simulation dynamics by actual vehicle dynamics. Okay, let me summarize. Here are the key takeaway. ROS Toolbox connects MATLAB and Simulink to the ROS and ROS2. ROS Toolbox enables data analysis, desktop prototyping, and deployment workflow. You can complement traditional ROS solution by combining it with MathWorks tool. ROS has a rich software infrastructure and vibrant user community. MATLAB Simulink offer rich tooling for application-specific particles and have a differentiator like state flow and BMB tools. To learn more about MathWorks robotics and ROS capability, please visit our product webpage on mathworks.com and download a trial to check out reference example. We have a robotic discovery page, user story, and video for further information. Don't forget to visit our MATLAB and Simulink robotic GitHub repository as well. Thank you for your attention.